So in this talk, I'm going to talk about Bitcoin's communication infrastructure and how hard is it to disrupt communication underlying the Bitcoin protocol. And right, so you can think of this if you've listened to the theoretical talks, I guess, earlier in the week, talking about synchrony and partial synchrony, and do we have asynchrony, are our messages dropped or not? Eventually that translates to something physical in the internet, right? There are signals going over wires, and there are concrete protocols that we chose to instantiate the internet with. And now the question is, how bad is everything? And if you've ever seen any of these talks about the internet, you probably know, right, that the internet sucks at doing secure communication, where you guarantee delivery of messages, right? It's pretty bad. So, like on a higher level, I want to kind of say proof of work and proof of stake on all those things, and having a set of identities and so on, got us past the Sybil attack at the consensus layer. We know, maybe, if you accept the assumptions anyway, networking still has all its insecurities. A lot of stuff you're going to see doesn't use identities, doesn't use keys, doesn't verify, doesn't validate, and it's susceptible, right? So in some other more deeper way, we didn't solve the Sybil attack everywhere, at every layer, and this is just a reminder of that. So let's go back again. I go back to the double spend attack, right? We have Satoshi's theorem that says this thing is not supposed to happen not with pretty high probability if the attacker controls less than 50% of the compute power. And the second assumption that is the one we're going to address now is that nodes can send blocks to each other and can communicate. It's very important in the protocol, right? So again, these are the two assumptions. And right, we talked about block propagation, that this is sometimes failing, and that's a problem. And now we're talking about attacks on network infrastructure, and there are attacks on the incentives of the protocol as well, which kind of relate to the fact that is the attacker really 50% of the compute power? We don't really know. Maybe he's small, maybe he's large, but we can try and make the network really large. So that's an incentive question that we're trying to do. So I'm going to talk about two types of attack in this hour. One is, I'm not going to talk about the internet. I'm assuming the internet is secure, and we're going to talk about Bitcoin's network formation. Nodes kind of find each other and decide to talk to each other. And this form of attack is called an Eclipse attack. It's a known attack on generally in peer-to-peer systems. And the other part would be about, right, the internet's insecurity in terms of routing and man-in-the-middle attacks, because Bitcoin transaction is actually, you'll be surprised, is not encrypted. So you could do man-in-the-middle attacks between nodes in the Bitcoin network. That's a kind of a sad thing. So I'll show you what you can do here and here. So each one of these is actually based on a paper that I worked with, in this case, people from Boston University, Ethan Hellman, Sharon Goldberg, Alison Kendler, and in this case, people from ETH, Maria Apostolaki and Laurent Van Bever, which were amazing security and networking researchers, are amazing security and networking researchers. And I want to talk about the general consequence of being able to break right, the ability of nodes to communicate, right? So we know that you can't have your liveness or your safety in some sense when you can't communicate. You can't have both. What happens in Bitcoin concretely is that when two sets of nodes can't communicate, one is building their own chain and the other is building another one, right? So we have a split. The guys building blocks here can't talk to the guys building blocks here. They're not aware of them. So one of the things that's going to happen, even if there's no attacker doing anything, right? At some point, the network will reconnect, and only one of these two chains will survive, right? One of these will be thrown out, one survives. That wipes out a lot of payments that happened during this period of time. They might be retransmitted later, but that's already a problem. There might be double spends living here and here. And if this disruption was allowed to take place for a while, maybe somebody thought his transaction was secure enough deep inside the chain, and they gave a product in exchange for money that is later erased. Okay, so another thing that happens is that the security for double spends is also reduced. Like the attacker, these chains are not growing at a very high rate again because the network is split in its power between them. So you could do double spend attacks on even transactions going further back because you're no longer racing against the whole power of the honest network. So, right, so we might have an attacker show up with a longer chain, which is would not have been long enough if all of these were on the same branch. So in some sense, attackers can do something more clever. They can try to balance these two chains. They can use some of the power of the nodes they isolated to double spend against the others. So this is a pretty bad thing in general. Right? So the general consequences is that even, of course, honest transactions are affected. There's also a lower block rate during the split. We're not mining at the same pace because there's less computational power. So we're experiencing lower throughputs. Maybe we can also not even send our transactions out between the two pieces of parts of the network. Maybe I'm in exchange. I've been partitioned away from the miners. I want to pay people. I can't even talk to the miners. Maybe the chain is proceeding correctly, but I can't even get my transactions into the blockchain. So all of these things can happen if there's no communication, right? So, and you could also combine with other attacks like selfish mining. Yeah.
You mentioned lower throughput. Is there a lower bound to the throughput or 0?
You could go to 0 if you, ideally, if you break each miner from each other, right? And everyone sending transactions from the miners, nobody can communicate, and there's basically no throughput, right? Essentially. Maybe Amin will tell you. Will you tell? Yeah. So this is Amin's work. An amazing piece of work that Amin has done. He'll show you basically an incentive attack on the protocol. This is how I say it. You probably have another way of describing that. So this thing also happens sometimes in regular systems. I don't know if you know. There are sometimes outages in payment systems. This is not about a network split, actually. There was a glitch in Israel. Somebody keyed in the wrong number, the wrong exchange rate from dollars to shekels somehow, and all of the credit cards in the country could not clear payments, could not settle payments for several hours until this problem was fixed. So we're going to talk about outages of this magnitude. And what really happened is that people were at supermarkets with loaded carts, preparing to pay for food. They reached the cashier. They can't pay because they don't have enough cash on them. They were expecting to use their credit card, and they just left shopping carts in the middle of the supermarket and walked away after 30 minutes of trying. Hours and hours won't go by. So this disrupts economic activity. Even having an outage like this, if Bitcoin ever becomes like a global currency, we manage to break it up in a way that does delay payments for hours. The system might bounce back again, but the amount of damage that we do in the meantime when transactions aren't trusted and aren't cleared is incredibly high. So we shouldn't be able to allow these things to run for hours at least, right? That would be our goal. And what I'd want to show you is that these attacks might actually get that. So we should start with the Eclipse attack. So now the idea of the Eclipse attack is to target the peer-to-peer network formation. And I want to tell you how do nodes connect to the network, at least in Bitcoin. And this is a general pattern for peer-to-peer networks. So let's assume there is some network already connected, and I boot up a new node. I want to connect. So usually what I have is I have a hard-coded address of either a DNS server or maybe one of these nodes that really is hard-coded into the code that I just downloaded from GitHub. And I connect to that, either a node or a DNS, and I get a list of nodes. So hopefully it's one of those nodes. And actually, this server, when I connect and request a list of nodes, it sometimes may also keep my address and serve it later to others. So this acts as a central point to bootstrap the network from, or to start it from. And then after I do this connection once, I start to connect to other peers here, and I get more IPs from them. And the idea is to never again connect to this DNS, because that's a central point that we overload if we have too many nodes. We don't want to talk to it too much. So it gives me a random subset. I connect to them. They give me more random subsets. So slowly I learn a lot about other peers. If I'm offline for a month and I come back, I start to try them. Maybe one of them is still alive. He'll give me more fresh lists that I'll kind of replace. So what I do with all these lists, I hold them in some buffer or some file. It's on my computer, and it's my local version. And this has some finite size that was configured into it. And what people typically do is they select connections now into the network at random, right? Because this builds more robust and more healthy networks that are good expanders and are harder to break up. And so you want to connect out, but still you limit the number of outgoing and incoming connections. Bitcoin nodes usually initiate 8 connections by default. The default is 8. So outgoing and incoming connections are really both symmetric. You can send and receive information on both of them. When I say outgoing, it means that this node initiated a connection attempt. So it initiates 8 connections to the network. It will also accept a certain number of connections that were initiated by other nodes. So the default there is closer to, I think, 120. I don't remember the exact number. So now I choose something randomly, I connect, and I'm part of the network. Right? So the main idea of the Eclipse attack is that I'm now the attacker. I want to partition this node from the rest of the network. So I'm going to connect to it with malicious nodes. I'm going to spam it with a lot of IP addresses. And the IP addresses are all attacker IPs. Right? And this is going to go into the buffer here. And it's going to replace all the addresses. And why does it replace all the addresses? Well, right, so it's fresher. So some of these might be offline, and newer information is in general better. That's a nice heuristic. Also, we have a limited space to store these things in. But even if we had unlimited space, and we added a lot of fake addresses, you would have to choose who you try to connect to first. Like if I buried the others down the list far enough, because I try to connect to fresh addresses first, that would also be bad for connectivity, right? So there's a limited buffer, but that's not the essence of the heuristic. Usually people just want to try to connect to fresh addresses. Now, if I did this sufficiently well, these malicious nodes can connect to the network, and they can filter any traffic that they want to this node. It thinks it's connected, it has enough peers, and then maybe it's not receiving all the messages, maybe it's not receiving blocks, and I can run this silently. I can be a buffer between you and the network. I also filter the lists of nodes that you get, so you never again hear of an honest node ever IP again if you are just connected to me. Every time a message like this goes through, I don't relay it. And at some point after 6 months of isolating nodes in silence and still giving them all the messages, I hit the switch and I attack. And I filter all blocks, and I start to do something crazy, like a huge outage for the entire internet. Right, so that's what you would do. That's the main idea. So the particulars, of course, really you have to go dig deep down into the details. Bitcoin has mechanisms that try to really overcome this. So here's the mechanism. This was a little bit obscure in the code. So this is a little bit of security through obscurity. There was this terribly complex mechanism, basically taking the peers table and partitioning it to 2 lists. One list is the tried list, where you keep IPs that you already managed to connect to. Okay, so if I try to connect to someone and he picks up the phone on the other side, he speaks Bitcoin protocol, then I keep him in the tried list. And there's the new list, which is just IPs that I heard about that I have not yet tried to connect to, or maybe when I called they didn't answer, right? So these are we're more skeptical about these. Now each one of these is partitioned into buckets that have 64 IPs in each one, smaller buckets. And the idea is that when you are getting a new message about some IP address, it's going to get mapped into a bucket. And the bucket that it's mapped into is based on some random seed that this node generated and a /16 address. So the /16 address basically means the first 16 bits of the IP address of the person. So the idea is, like, if you have similar addresses that have the same /16 prefix, they're going to map into the same bucket, and they might evict each other. If something falls into your slot in the bucket, you evict whoever's there. So the idea is, like, if I have an IP address with some internet provider, I can disconnect, reconnect. I might have another IP address now, but it would probably be from the same /16. And if I send you two messages, one from this and one from that, then maybe I want to evict my own old message. That tries to get the attackers to kind of collide with themselves and to evict themselves. And there's a similar idea in the tried table. So you're using the /16 of the IP and the /16 of the reporting nodes as well, and so on. And there was another rule in Bitcoin that says that when you evict something from one of these buckets, you need to choose one of the IPs to kind of throw out. You use you throw out the older one, right? You want fresh addresses, so you bias the decision on what to evict based on the age of the message. So here's the idea for the attack. Right? How do we attack each of these tables? So for the tried table, you only make it in here, I remind you, if you are actually someone that this node connected to. So what we do is we form many incoming connections to the node from different IPs. And so at each time we form a connection, your IP gets into one of these and you evict something. So that's the strategy. For the new table, it's even easier. You just use different nodes to send lists of IP addresses that are all bogus. They're from unassigned ranges from the IP space. There are areas that don't even belong to Bitcoin nodes. You can just give any address you want, and you give a lot of them, and you try to overrun this. Right? So you just broadcast a bunch. And this really then becomes a game of coupon collector. If you think about it, every time you send something in here, you hit, you might be lucky and evict an honest IP address. And when you've evicted all of them, the node is basically successfully attacked. When it will reboot and it needs to try to connect to the Bitcoin network again, it will connect only to attacker nodes. It might try to form connections to nodes that aren't even Bitcoin nodes, so those will fail. And eventually it's partitioned. Right, so it's owned by the attacker. So the parameters that were chosen for Bitcoin were surprisingly bad. Right, you need to hit enough each bucket enough times. So here's the numbers of addresses we managed to insert. This is the number of addresses that was actually kept. The more you try, the better off you are in terms of monopolizing Bitcoin. And it turns out that Bitcoin's eviction policy, which is here in green, is worse than if you had just done random eviction. Because you're evicting old addresses, the attacker is spamming all the time, so all of his addresses are new. The old addresses are actually the ones you wanted to keep. So that's worse than random eviction, right? And for initially empty nodes, it was even worse. So that's the basics of that attack. Now I want to switch over to the second attack, right? So this was assuming that internet messages still pass. I just attacked the peer-to-peer protocol. The second attack is going to be based on. So we suggested some mitigations, basically make the buffers slightly larger, remove this bias for all addresses, and that actually made it into the protocol. So this bias for all addresses, for example, is something that they were happy to accept because you just make the code less complicated, and it's provably better. Right, so last in first out may have been also good, but I'm not sure, because then you kind of suffer from the freshness issue. You keep all the old addresses, not the fresh ones. So I think it's an interesting question to answer how to do this eviction properly, and I actually have a student that's worked on a paper that tries to answer this, and there was a game theoretic analysis of what you want to do versus the attacker. So. You don't hurt security, but you pay for it with other resources. So every connection that you have actually costs a lot of memory, because nodes apparently remember the transactions that they sent over the link to each connection, so they don't rebroadcast to avoid all sorts of things. So there are a few megabytes of RAM that are allocated per connection. So if you have thousands of them, that's going to be a problem. You have 8 because if you make this number larger, the number of incoming connections on the other side also gets to be larger. It's harder to get messages over. Everybody, when they have a new block, they send all their neighbors a message saying, I have a new block. So if you have 120 neighbors, you're going to send 120 times, I have a new block. Some of them will request it. When they request, maybe you got too many requests at once to serve, and they are not requesting from someone else at the same time, so that delays block propagation a little bit. So there are all these issues and trade-offs that come into play, that you want to have a good number but not too high. Yeah, or you take a lot of resources from the network to be better secure. So I will say that miners don't keep the parameter of 8. They obviously do change it. It's very easy to change. You don't have to recompile the code. It's some value in the configuration files, in the config files. Okay, but let's move on to the second attack. So here, this is maybe I should first start with a story about an attack that did happen, actually took place. Apparently, some attacker managed to redirect the traffic from 19 different internet providers. And he managed to steal bitcoins this way. Right, so this was a story in Wired. And the amount of coins that this guy stole was $83,000. So what did he actually do? He hijacked the traffic from these providers and pretended to be a node that's a miner. Right, so if you recall, we talked about this. This is the structure of the Bitcoin block. When you have a mining pool, right, and this is the thing that you hash to create a legal Bitcoin block is just the header. So when you have a mining pool, right, miners can join together and talk to some server, the mining pool server, and what they really do is this server gives them a block header. They do a lot of hash computations. And they send back the nonce that kind of solves the problem of creating a new block, and then they split the money, right? These guys get some money, but the mining pool also gets fees after it publishes a block that was created here. So what this guy was doing, right? The mining pool really has some IP address. These guys are trying to connect to the mining pool over the internet. The attacker shows up, hijacks this traffic, and actually gives them a header, a block header to work on. And when they give him the answer, he publishes the block and takes all the money for himself. Okay? Or he can even redirect it into the pool under a different name and then get the profits from the pool, because he's working from the pool. He identifies as himself, not as the others. So he routes traffic through him. That basically gives him the ability to get the rewards whenever they find a block, and he stole $80,000 for doing that. So you might ask yourself, so how do you do this when this guy is trying to connect to a certain IP? How do you get his traffic? And maybe that's really, really hard, and it's very expensive, and it's impossible to do. And for that, you need to know a little bit about the BGP protocol, which is the routing protocol that kind of connects the internet together. So each one of these nodes now is not a single router. This is an autonomous system. So an autonomous system, you can think of AT&T, or the Hebrew University could be a small autonomous system. But there are autonomous systems that are connected through the internet. Inside each one of them, there are many routers, but they are routing based on some other protocol. But in between them, right, the glue that holds this network of networks together is the Border Gateway Protocol, BGP. And BGP works as follows. If this autonomous system has the IP range 192.56 something something, it announces it to the world. So all the servers that have this IP are actually sitting here. It announces that to the world. And then, right, the neighbors of this autonomous systems have a router that says, okay, here's my routing table now. If somebody tries to send a message to an address looking like that, this has this prefix and whatever you want in here, I forward it to this autonomous system, right? And what they do then is they forward this. They say, I forward to this address via autonomous system 1. They send this message to all of their neighbors. And they might say, okay, now I'll route through you to that address. And they announce that message to other neighbors, and so on and so forth. So eventually, everybody has a routing table. And this is, how the internet routes. Now, the problem is that we might have an attacker right here. These guys say, I have this IP range. And the attacker is going to say, well, actually, I have 192.56.129. So you might notice that this is more specific than this. So it's a more narrow IP range. So this is a /24 address. He's giving 24 bits. And this is /16. And now what happens? Right, this guy is seeing two announcements. This guy said, if you have this prefix, you route here. If you have this prefix, you route here. So he puts both of them into the routing table, actually. And when it's time to send send traffic, where does traffic go? If it matches the more specific range, it'll actually go to this autonomous system. Always, right? So the rule is that you route to the most specific prefix. So this guy could actually do several announcements, by the way. He could announce 192.56. The first bit is 1 and star whatever. And the first bit is 0 star whatever, route to me. And that would completely hijack all of the traffic here because it's more specific, these two announcements together. So eventually the attacker's message propagates out, and you have all of the internet, not part of it, all of the internet routing messages to him on an IP address that isn't really his.
But won't AS1 know that?
AS1 finds out eventually. He receives messages saying there's some weird route to going here. The question is, what do you do to fix it? Right? AS1 is helpless to fix this. He's already giving out announcements. AS1 can try and give specific announcements of this nature. So he's going to partition the internet. Some will go here and some will go there. It's still pretty bad. It takes a while to figure it out, and you need manual intervention to reconfigure routers.
There's no authority to complain to with this false announcement?
There's unfortunately no authority to complain to because the internet is spread over the world, right? So one very famous incident that people like returning to is that a server in Pakistan did this. Somebody in Pakistan decided to censor YouTube. They didn't want Pakistanis to watch YouTube because of all the vile things you see there, like cat videos and so on. And they configured a router to take, they wanted to take all Pakistani traffic that was going to YouTube and just throw it away. So there was a router that claimed to be YouTube, and it threw all the traffic into basically dev null. And then they said, okay, we filtered YouTube. The problem is that the message propagated out, and YouTube had an outage of several hours around the world because of one Pakistani router. Okay, several hours. And the way you stop that is by calling people on the phone and saying, these guys around him maybe, saying, this guy is misbehaving, you should filter those messages, and then the internet goes back to normal. It takes human intervention.
Why doesn't it happen every day?
So that's an excellent question. Do you know why? Because it's on the next slide. Hijacks are super common. So Laurent, who's one of my co-authors on this paper, who's an amazing networking guy, looked at logs from BGP announcements, and he analyzed them over a period of several months. And you could look at addresses that kind of switch over to a different autonomous system and then come back after a few hours. You can say this is probably a hijack attempt because it's unreasonable that somebody sold an IP and got it back a few hours later to a different place. And the number of hijacks that we get per month is on the order of hundreds of thousands of addresses of events. These are hijack events. So each one of them hijacks a range of nodes. So these actually happen all the time. Right? So the number of prefixes that are hijacked at once is also very high. This is in the thousands and tens of thousands for each event. So some of these are malicious attempts to grab your traffic. Like you think you're connecting to your bank. Maybe somebody hijacked traffic to that bank. And you're actually connecting to an attacker. So you should be aware. This is why we have certificates when we connect to banks, and you have that green lock in your browser, hopefully. But most of these cases are just configuration errors. Somebody screwed up and typed something wrong into the router, and he's propagated the message to the internet, and there's an outage somewhere else. Suddenly, YouTube is offline for some reason. And it turns out that when you look at these logs, some of these hijack attempts are for IP ranges that really house Bitcoin nodes. We can actually tell what is the list of Bitcoin nodes because you can connect them via these mechanisms we talked about in the previous part of the talk. So it turns out that this was actually affecting Bitcoin nodes as well. I mean, you're hijacking prefixes all over the internet. Sometimes there are nodes that are there. So hundreds of nodes are actually getting hijacked every month. And you don't read about it in the news, right? So then what we did was we hijacked our own node. So just to see how fast it'll happen and to show we can. So we connected the node to the regular Bitcoin network. We put it on a special IP range that is used for exactly these purposes to test these things out. And then we hijacked that specific address. So we disconnected our node from the Bitcoin network. We repeatedly did it. So that took maybe 60 seconds to get all of the traffic, all of the links going to that node into our machine instead of to that node itself.
How did you announce your IP?
So we had a more specific prefix. So this was, I think, stored.
More specific. How did you announce it?
So you need a router. You need access to a router somewhere.
So you have to break into a router.
Yeah, you have to break into a router or to own a router. So I think the guy who actually stole those bitcoins that I told you about before from the pools was some employee in an ISP. So he has access to the routers. He configured a router, and there are compromised routers that you can get passwords for, just like you can get passwords to people's access to people's computer via botnets. So you need access to a router. That's not very hard. There are a lot of routers out there. Some of them are really, really old and maybe obsolete and maybe unsecure. While it takes us 60 seconds to hijack your traffic, it takes hours to repair this back because this again needs human intervention. So now we said, okay, let's look at what we can do with this. We can start to hit mining pools, and mining pools are actually right. We're gonna have these Bitcoin nodes who are somewhere in the internet. Some of them are miners. Miners are actually sometimes connected to several internet providers just to have more security in their communication, which is a good idea. And they're running back-end protocols, and they're using something called the Stratum protocol to connect to their miners. And so as you know, there aren't a lot of pools. This is maybe an old depiction of the hash rate distribution from when we were working on this paper. So all you need to do is hijack a very small number of addresses just to attack the pools that are there, to partition them from everybody else and maybe from each other. So the attack itself, if you wanted to isolate 40% of the mining power, you could hijack maybe something like 37 prefixes. Am I looking at the right row? And the median was 80, and you could do 8 different partitions of the network that would give you 40% of the mining power isolated from the rest. So given the high number of hijacks that we've seen before, this will just hide within the level of traffic hijacking that happens today, and nobody would notice it except, of course, these pools. So this is pretty bad, right? Most of the nodes are not advertised in /24 prefixes, so they're in more general prefix, and so you could hijack all of the traffic. 7% of the nodes we found were in the most specific prefix possible, which is /24, so you can't hijack all of the traffic to them, maybe just half of the internet. That's already bad, but I think the situation is pretty bad to begin with. Now, partitions themselves have to be perfect. You may have the intuition for this. Once I break the partition, I have a single link crossing it. That's already good for me. So we had an algorithm in the paper how to detect these leaks and refine our hijacking attempts, actually. Let's see if we have time. Yeah, we have 15 minutes. So the next thing I want to show you is a different attack. Yeah.
So you said there was hundreds of these a month, right? There was like
thousands, yeah.
Yeah, for Bitcoin. And you said it
For-
takes
yeah.
hours to fix them. I mean, can these people working in the ISP do anything else than sit and try? It seems like that's
So-
ready to be able to be fixed.
So people are working on systems that detect these and monitor these and fix them faster. But basically, the right answer would be to, when somebody announces that they're a certain IP, they should provide some certificates saying, I really was assigned that IP. And there, surprisingly, or not surprisingly, there's a protocol that does this. It's called Secure BGP, SBGP. And you can switch it on. It's built into every new router that, every time Cisco sells a router, of course, they have BGP and Secure BGP already enabled in it, just like they have IP version 4 and IP version 6. But the protocol doesn't give you any benefits if you deploy it alone. So if I switch it on my router, but the rest of the route doesn't check signatures, doesn't do any verification, it's useless. So nobody bothers. And the result is that the internet remains unsecure, and Secure BGP is just not deployed anywhere, or literally anywhere. There's a small percentage of nodes of routers that actually do have it. Yeah.
If we use blockchain
I don't know. Yeah.
Ways to check if a router has enabled Secure BGP?
I'm not. I don't know enough of the details to tell you, but probably yes. Yeah, probably yeah.
So what would happen if nodes refuse to interact with nodes that haven't?
They won't have a connection to the internet. That's the basic answer, which is pretty sad. The other thing I want to show you is man-in-the-middle attacks, and I think this is really cute because this shows you why you should encrypt your traffic, which is kind of a dumb thing to say, or maybe an obvious thing to say. So here's the protocol for Bitcoin, how Bitcoin blocks are sent. So let's say I just created a block, or I received the new block. I'm the sender. So I announce the fact that I have a new block. I send what's called an inv message to my potential receiver. I say, here's the block I have. That's the hash of the block that I just have. And this guy says, get data. Please give me this new block. And he gives the hash of the block that he wants. And then we transmit the block. Right? So hopefully everything works. Now, you don't do this you don't request a block from everybody. Usually when you're a node, you receive several announcements that the new block has been created by each one of your neighbors that when they hear about it. and then you just request from one. You send a request to one of them. And you need to remember, right, so traffic is not encrypted here. And there's another peculiarity that happens if you send a request for a block and you don't get a response for 20 minutes, you drop the connection. You say, this guy is trying to stall me. I disconnect from him, I connect to some other node. So this is the Bitcoin protocol. Now here's how we propose to attack it. So you could be, there are two options. Maybe you're a man in the middle. You could be sitting in some internet service provider and this traffic is running through you. And now you can only see the traffic from the sender to the receiver, but not the traffic going back. So what you should also know is that when you route traffic on the internet, the traffic to the receiver could be routed differently from the traffic from the receiver to the sender. It could be a totally different path. So in this case, you sit on the path from the sender to the receiver, but not on the other direction. So when this guy sends an inventory message saying, I have a new block, right, you let it through. This guy is requesting a block. That's great. And then the block is sent. Now what you do is you tamper with the block. You make it invalid. Right, you just change a bit there. So you have to make the Bitcoin protocol not validate the block. Maybe you hurt a signature, but you have to pass the networking layers CRC checks, and so and that's still very easy. We actually implemented that, so we know. And then 20 minutes later, this guy drops the connection, but in the meantime, he didn't ask for the block from someone else. He's still waiting to get that block from us. So we just delayed block propagation to him by 20 minutes. So think of a miner that did not hear about the latest block for 20 minutes. The thing that he's mining is going to go to the trash, right? He's not mining on the most recent version of the blockchain, right? This goes goes out. But on the other hand, we lose the connection. So maybe next time we won't be on path. So that's not a great thing for us as an attacker. We want to do this again and again. So if we're on the path for a lot of these, maybe we can do some damage. Yeah, there's a question. Yeah.
So why does the receiver, so the receiver receives an invalid block and checks that it's invalid. Why doesn't it drop the connection? Because the Ether is obviously misbehaving by sending invalid blocks.
So it doesn't. I don't know why. That's a good question. It just doesn't. And it doesn't know that it would have been the block that he requested because it doesn't look like the same block. It doesn't have the same hash. It's not the same block, right? So you can hurt.
So I ask for data with a specific hash. I get some garbage and I say, okay, I'll just wait.
Yeah, that's what's built in there, unfortunately. Yeah.
In this case, why just not blocking the block from coming?
So why not block this inventory message?
No, the invalid block. We're sending it in the distance.
Because dropping is hard. This guy is sending something. He's expecting ACKs, right? An ACK, and then the ACK is going over another route that we don't control. If we really drop the packets, the connection will be dropped here, and we actually want to. And when the connection is dropped, he'll make another request for the block, and we don't want that. So we want to keep the connection alive, but just make him think that we're working on serving the block to other people. We'll get to you in a second, but really it's 20 minutes, and you're not getting the block. Right? So that's what we want to do. Now there's a better attack if we're on the other way. If we see traffic from the receiver to the sender, we're on path from there to there. So this is what we do. This guy sends an inventory message saying I have a block. Now we see this traffic really. We see a get data request, a request for a specific block. So what we do is we alter the request along the way. We change it to the hash of another block that really does exist. Maybe it's in even an old block, somewhere deeper in the chain. And this guy sees this request. He says, okay, I'll send you that block if you want. Or maybe an invalid block that doesn't exist. So there could be a transmission here, or there could be a block that I've never heard about. I don't know what to do with this message. I can't send you anything. But anyway, now we wait for 19 minutes. The connection is about to drop. The issue, what we do here is there are always messages, get data messages that are going from this receiver to this sender all the time, because get data messages are also used to request transactions. So there's an inventory get data thing for transactions when they're sent. So this guy is asking after 19 minutes for some transaction, which occurs very often, like 3 times a second. We change that back to the block. We say, okay, now you're actually requesting the block. You get the block here 20 minutes later, before 20 minutes elapse, and you don't drop the connection. So we delay the block 20 minutes. The connection is still there. We can do it again for the next block that you request through us. Right? We can repeat this again and again because the connection is still live. This node is still considered trustworthy. Yeah?
Why can't you just do that when you get the traffic from the sender, that around the 20 minutes you just send the block?
So what I wanted to do is to intervene with one small message where I keep the same message sizes, everything, because later intervening with all future messages would be really hard. If I want to keep a connection, the TCP protocol has counters and so on that I have to do, and I didn't want our man in the middle to have to do anything. So this is a stateless man in the middle. He doesn't need to remember anything about the connection, maybe except for this hash and a timer. So you kind of interfere here with the message. Everything else, you let all the other traffic go through you without ever having to process it in your CPU and do anything complex with it. And you only do some processing for this. And we actually implemented a man in the middle that could listen to a whole lot of traffic, pull out a specific packet that it wants to change it, put it back in, but there's like a river flowing through it. And it could handle this attack simultaneously on many, many, many different nodes that are passing through. Because it was stateless. So it was very cheap to do this attack. And it delays, for each one, or each of these packets that you change, you delay someone's block arrival by 20 minutes, right? So you might ask, how efficient is this attack? Let's say you want to have a victim that, right? So that you intercept 50% of someone's connections, right? So you are on the path of 50% of his internet connections. You keep him uninformed about the latest block for 63% of the time. So the great majority of his hash power is wasted on stuff that's irrelevant. And 67.9% of the nodes actually are in this situation where there is an autonomous system that sees half of their traffic that is not their provider. An autonomous system who's not, your provider sees all of your traffic. Somebody who's not your provider who sees 50% of your traffic, that's the case for a large number of nodes. So this is really bad. So the mitigation is, of course, to encrypt, right? Encrypt the connection. Then we can't do all of this stuff. I mean, this is very basic. Use certificates to identify pools. So when you connect to a pool, somebody hijacks your traffic, you should know that you're connecting to the pool or not. That's very basic. And still it wasn't there. You want to have a lot of stable connections, right? If your connection gets changed or dropped or rerouted, maybe you're connecting to an attacker now, if you go back to the Eclipse attack case. But you also do want to have some connections keep changing and some connections that are more stable over time. There's like a mix that you want to do. And there's more research that you need on how to do eviction, how to better secure this protocol. So let me kind of reiterate the message again. Bitcoin is secured only if nodes can communicate. And communication in the internet is really easily disrupted. So we need to do a lot more to secure the network, right? So if you're running your private blockchain on it or your public blockchain and the infrastructure that you build on is so easily disrupted, you have to rethink what it is that you're doing. All right. Yeah, there are questions. Yeah.
How much harder would this be if you pulled block information from all your peers?
So if you started doing things like more advanced peer-to-peer protocols where you start to get parts of the block, you would probably do better in this sense. You don't wait for everybody. If you request a piece from somebody and you request another piece from somebody else, they finish, then you switch to that guy to request this, the same piece again. On the other hand, your block propagation time starts to grow because you start to do all these crazy things, and you look for missing pieces, and you also need to make sure that when somebody serves you a piece, you do error correction on that, so nobody sends you fake pieces. This was an attack against peer-to-peer systems as well. So there's a whole way to build these systems to do that, but it takes different trade-offs. It becomes a little bit hard. There's a lot of literature on peer-to-peer systems and how to send information through them from the early 2000s. I guess it's relevant again, and as a basis for Bitcoin and other things. Yeah. Sorry? No, there's a proposal to do it, but nobody tried yet. So when people ask me how expensive would it be to break Bitcoin, right? Would you need to buy a lot of mining equipment and double spend the network? The answer is no. What you do is you do a traffic hijacking thing. You break up the network into small pieces that don't communicate, and that's a very cheap attack. We didn't have to spend a lot of money to break up the internet in that sense. Yeah. Why do we think nobody's done it so far? So the thing is, this is not directly monetizable, right? You could short Bitcoin and try to do these things repeatedly. There's a chance you'll be found out, but you don't immediately gain money. I mean, if you steal, you destroy something, you can break something. That's fine. So you'll break it for a few hours at this point in time, and then maybe more defenses will come in, right? So I think nobody did it because nobody bothered. That's maybe the answer. From our experiments, I mean, we isolated our own nodes. We saw what we need to do to isolate other nodes. So from our own experience, we could have actually done it ourselves if we wanted. I mean, to break Bitcoin in many, many different ways, in many partitions. The Eclipse attack is also something we implemented. We had code running, and we isolated an actual node that was connected to the Bitcoin network, which was our own. We spammed it with false IP addresses, and we got it to connect only to our own nodes as attacker nodes. So these attacks were actually running. I mean, they're definitely possible. Yeah.
So what are other blockchains doing?
Other blockchains are pretty much copying Bitcoin's code or writing something of their own, and I don't think there's more knowledge in the peer-to-peer layer that's doing better. People have done hijacking attacks on Ethereum as well. I mean, Eclipse attacks on Ethereum's system. So there's another paper that did it on Ethereum. I mean,
so I should read your new paper if I want to know the state of the art.
So yeah, there are no good answers here. What you'd really want is you want to cryptographically secure these things with certificates and with keys
but
and.
You also want to be fast, right?
Yeah, but I'm talking about the networking layer and right. So for the peer-to-peer network formation, you're in a deeper bit of trouble there. I think for the Eclipse attack, somehow it's more inherently problematic. Maybe there's a way to leverage off the fact that you're already doing proof of work to make sure that you're not allowed to spam too many IP messages. But we did have more mitigations in like this newer paper that did better there. Yeah.
So how would you endorse the PKI you need for certificates in this case?
Sorry?
How would you endorse the community infrastructure to be?
For the hijacking case?
Yeah, how would you organize it? Because you don't want to trust a certificate and
No, so you do. So for the internet, there is somebody who eventually assigns a certain IP range to a certain autonomous system, and so there is a root of trust. It's all about so it's not decentralized, right? There is a root of trust. Somebody says this IP belongs to that autonomous system and not to that one, and you just need this guy to sign a certificate. For the peer-to-peer system, maybe it's harder, right? There's this DNS server that is a point of failure that's central. Maybe you can build off of that, but that could also be DDoSed and attacked and broken into and so on, right? Yeah.
For the Eclipse attack, the problem is that we don't know the state of the network, right?
You don't know you don't even have a list of participants of the network.
For example, one could do something like in Tor where they have directory authorities and every hour they give a consensus of the state of the network and then know what the network is. And then
But then you need to know who they are, right? So if their addresses are hard-coded, then an attacker also knows them in advance. He can try to compromise them. He can try to bring them down. He can try to hijack traffic to them. to disconnect you from them, right? To the authorities. You can try to make you not connect to the authority to ask which are Bitcoin nodes, right? So you could combine all these attacks. It's a hard question to solve, right? It's a hard problem to solve. So in some sense, we do something in the higher layer that gives us consensus, but the lower layer is still very shoddy, right? So that's the main message. Thank you, everyone.